pleasure to have Hannah Diamond-Lowe here. I think I first met Hannah when she was actually an undergrad at the University of Chicago. After that, she got her PhD from Harvard University. We overlapped there, so that's when I really got to know Hannah. And then she went off to Europe for 4 years, to Denmark, to the Technical University of Denmark, where she was a postdoc and a research scientist. Now she's an assistant astronomer at Space Telescope Science Institute. For the non-astronomers in the room, that's the people who run the Hubble Space Telescope and also the James Webb Space Telescope. On the James Webb Space Telescope, Hannah is running one of the large programs called the Hot Rocks Survey. And I think she's going to tell us about that today. So take it away, Hannah.
All right, thank you so much, Taylor. Oh wow, applause for it. Thank you so much for having me. I've already met some great people here. It's like a really good department. And I am here to talk about hot rocks and their host stars. And this is the main focus of my research, the sort of terrestrial exoplanets and the M-dwarfs they orbit. So we're going to start by putting into context what I mean when I say rocky planet. This is a pretty obligatory figure in most astronomy talks, but if you're not familiar, this is the number of exoplanets that we've discovered. It's almost 6,000 now. And these are plotted by planet mass in Earth masses, and then as a function of the orbital semi-major axis. So that's how far the planet is from its host star. And to kind of guide your eye, we have over here Earth at 1 AU, and a massive 1 Earth mass. And what might be apparent just from looking at this quickly is that the part of parameter space where the solar system planets generally sit is not the part of parameter space where we've discovered a lot of exoplanets. We don't think that this is a sort of true underlying understanding of what kind of exoplanets are out there. This is an observational bias. It is much easier to detect more massive things that are closer to their host stars with the various methods we use to detect and characterize planets. So we try to make these sort of broad categories out of this massive data points. And the sort of massive planets very close to the host stars, those are generally called hot Jupiters. I'll show you they're actually not so common in terms of total planets, but they're the easiest to detect. So we've done a lot of really great work honing our techniques on these hot Jupiter planets. Then you can have sort of warmer, cooler Jupiters, getting close to kind of the parameter space of our own Jupiter. And then my research sort of goes down into this area of sub-Neptunes, or some people like to call them water worlds, and also these kind of rocky planets. We're going to start kind of zooming in on that area. So if we change this plot, so now we're only focused on these smaller planets. We have planet radius as a function of, Earth radii as a function of planet mass and Earth masses. And if you just looked at this mass radius diagram, you would think, my math's very cool. You would think that, oh, there's just way more gas giant planets. But again, this is that observational bias showing up. If you look at this histogram down here to the right, this is actually the planets detected by radius. And we can have we're a lot more sensitive to smaller planets with this method. And so this is closer to the actual true distribution, which is we have a lot of really small planets that we've detected. It's just really, really hard to measure those masses. And you need a measured mass to show up on this plot. We're going to zoom in even a little bit farther down to the actual small planets, so up to about 4 Earth radii. And I've actually added here some compositional curves. So these are just bulk compositions. We don't really know the sort of interior structure of these planets. But you can project out densities if you have a mass and a radius. And so you can see here, this is the sort of 100% iron line. We don't see a lot of things below that. It's really hard to form a pure iron planet. And indeed, we have not detected one. And then you have Earth composition, and then you can start adding some water. You can start adding a little bit of hydrogen, helium, and puff up that atmosphere. And so there's some sort of ambiguity in this parameter space. But generally, we talk about sort of sub-Neptune exoplanets that have this hydrogen, helium envelope. And then you have these kind of rocky planets, which do not have a hydrogen envelope. They may have atmospheres, or they may not, but that's the sort of bulk composition aligns with this Earth composition curve. So that's where we're heading, rocky planets, for the rest of the talk. One thing I do want to point out is that we also have the solar system planets on here. So in the bottom left corner, you can see Earth and Venus. And according to this figure, Earth and Venus are exactly the same composition. And indeed, they are about the same size and mass, but there's they're very distinct planets, right? Venus has about 100 bars of CO2 on its surface, and like noxious clouds. Whereas Earth, we live here, we breathe the air, it's great. You cannot just exchange these two, and how we understand planets. We can't just go land on Venus and live happily there. So even though if these were exoplanets, we really couldn't tell the difference. There's actually a lot to try to understand between what is an exo-Venus and what might be an exo-Earth or something else entirely. One other thing I want to point out here, if we look at our neighbor rocky planets, is that all of them have some amount of CO2, which is a very common molecule, and that's maybe going to come to our advantage later in the talk. Okay. So to really differentiate what is a Venus, what is an Earth, what is a Mars, or something else entirely, we really need to probe the planet's atmospheres. It's not the only difference, but that's actually the one that's most accessible after just measuring a mass and a radius. We would love to get seismology and interior structure, but this is what we can do now, or we can try to do. And so this is where we were in circa about 2022, 2023. So this figure, I'll show it a few times in a few different ways, so it's worth explaining now. The y-axis is this concept called the transmission spectroscopy metric, which was developed by Eliza Kempton, which is basically saying that planets higher up on the graph are easier to observe, planets lower down are harder to observe. And then they're arranged on the x-axis by how far the systems are away from us, from the sun. And then the color coding is equilibrium temperature. And up until data from James Webb really started coming down, all we could really say is, well, we've looked at these planets and they don't have hydrogen helium atmospheres. Spent a lot of my PhD doing this. Now, is that a particularly interesting result? Maybe. We didn't really expect them to, but it's good we looked, and I got a degree out of it. But now we can start doing something a little more interesting. We can actually try to detect heavier atmospheres that we might expect could exist on these planets, not a poofy puffy hydrogen helium atmosphere. I will say so far, and I know we talked a little bit at lunch about this, so if you want to fight me on it, I'm here to hear that argument. But I would say we've not definitively widely accepted in all areas of the community. We've not definitively detected an atmosphere on a rocky exoplanet orbiting an M dwarf, or any other star, frankly, but M dwarf specifically. You can look at this paper that has potentially detected an atmosphere around 55 K3e, which is a super hot planet orbiting a G star. I'm not here to talk about that. It's a good paper that you should read it. So why this M dwarf qualification? This was a phrase my advisor, I think, coined, where there's this concept of the M dwarf opportunity. So if you want to detect a small rocky planet, it helps to go to a small star. And this is true both for the two main detection methods, which is transits and radial velocity. Whichever one, it is more helpful to have a smaller, less massive star when you're looking for a smaller, less massive planet. Your ratio of those signals is just going to increase. So for example, if you look at the bottom with a transit signal, this is just illustrative, but where you might have looks like a pretty significant detectable transit signal around an M star, that's going to get way, way smaller around a G star. There's also a few other advantages, which is actually M dwarfs are incredibly numerous in the stellar neighborhood. So if you're waiting for that really nice alignment for the planet to pass in front of the star, from our perspective, you just get more chances, just statistic. There's fewer nearby G stars, so your detection probability goes down. okay, so that seems great. So how do we do this? How we detect and characterize planets, I would say, comes in three main flavors if we're talking about planets that transit their stars. There's a whole field of direct imaging that is also doing some great work, but this is really where we're at for rocky planet. So we're going to start with the transit method. This has been done for many years. I think maybe you've probably heard of the transit method. So I'm not going to go into the history of it. I'm just going to say, wow, look at these transits with JWST. So this is the planet GJ486b. I'll actually come back to talk about this system a few times. So I know that letters and numbers can be annoying to remember, but if you're just going to remember one, GJ486b is a really cool planet that has a really interesting star. These are transits from James Webb, and the quality of this data is what we were getting for hot Jupiters pre-James Webb. So the fact that you can go an order of magnitude smaller in planet size and then get data of this quality, it is really amazing. Another way I like to say that is, so these maps on the left here, this is actual data. So time is on the x-axis, and then you're actually getting like the spectrum spread over a wavelength on the y. I'd never seen a figure like that for a rocky planet before James Webb. You just couldn't pull out the actual transit from the noise. And I'm saying all this to try to, if you needed any convincing, just what a powerful telescope this is. And that I hope will prepare you for how hard it is to still do what we're trying to do for rocky planet. Okay, so we can see the transits. That's awesome. Look at this huge signal. M-dwarf opportunity is working. And they can take that spectrum and make a transmission. They can make a transmission spectrum. So this is the transit depth as a function of wavelength for this planet, GJ486b. And this is from a really nice paper by Sarah Moran et al. In 2023. And what you can try to do here is say, well, here's some forward models. We've put some kind of pure atmospheres around this planet, and then we can do some sort of chi-squared statistics. And you can see that the no atmosphere flat line has a reduced chi-squared of about 1, so that agrees with the data. But what this paper sort of said, is that the water feature actually agrees even a little bit better. So is there water in GJ486b? Well, I really like this paper because they did a really thorough job and actually ran a retrieval where they were able to include, they tested 2 scenarios. One is that, yes, this planet maybe does have water in its spectrum, and you can get an abundance of water that seems to agree. Or you can put some star spots on your M-dwarf. M-dwarfs are cool enough that water is present in the M-dwarf spectrum, and that is coming from these cooler, we think this is coming from the cooler spots on the photosphere. And they showed that you could equally well fit the data with a star spot model. So there's water, perhaps, but whether it's in the planet or whether it's in the star is completely inconclusive. And this is the problem with the transit method for rocky planets, especially, is you have this, this is a term that was called the transit light source effect, which is basically saying that, we cannot resolve the surface of these stars, but yet they are not homogeneous, the surfaces. So when a planet is passing in front of the star, you actually don't know what fraction of the stellar light is being blocked because you don't know what is behind the planet. If the stars were completely uniform, this wouldn't be a problem. We could get our water detection, we'd be so happy. But that's actually not what we can do. And you can measure, you can model rather, the effect that this has, and it gets worse and worse as you go into the sort of optical and near infrared. So this is the downside of transit spectroscopy. So here's our M-dwarf opportunity, and now it's more of a question because you have these cons that M-dwarfs bring, which are stellar activity and these cool spots that can really mimic water. And that's important because that's a main spectral feature we would be hoping to find. Water has a pretty big signal to noise feature. If you want to look for like really like CO2 features, that's starting to get a lot harder. So water was like our first thing we could really try. but it's very contaminated. So that actually makes sort of larger, hotter stars look a little more appealing, but they still have those drawbacks. Okay, so transit is sort of the first thing you try because it's easier to do and it doesn't use a lot of telescope time. But there's these two other methods that are starting to come to prominence now with James Webb. I'm going to start with the phase curve because you get the most information out of the phase curve, and this kind of just makes sense. You just get more data. And so if you have, all this extra data, you can start pulling out some different measurements. So this is actually 55K per E, and even though I said I wasn't here to talk about this planet, this paper illustrates really nicely this point. So instead of the planet to star radius ratio, we have the planet to star flux ratio as a function of orbital phase. And I've kind of labeled here, we usually call phase 0, that's the transit. And then as the planet goes around and goes behind the star, that's phase 0.5. You have a circular orbit or a little shifted if you don't. And there's two things that you can really measure from here. One is this maximum flux, so you can see where this peak flux differs from the trough of the phase curve flux. And that difference can tell you something about the atmosphere. You can also get an offset in the peak brightness. So if nothing was moving, if no energy was moving from your substellar point around to the other side of your planet, you'd expect that when the planet goes behind the star and the full day side is facing you, that you would have this dip coinciding exactly with the maximum flux. But because you don't see that, this paper suggested, this meant that there was some fluid moving that hot spot kind of closer around to the night side. And an atmosphere follows fluid dynamics. So that was the kind of theory here. But do we need a phase curve? The problem with a phase curve is that it's really expensive. So maybe you can do this for a really hot planet that has a 16-hour orbit, but we want to study planets that have 5-day orbits or 10-day orbits. And while I think it would be a great use of JWST time to stare at planets for 5 days at a time, that's really hard to get through to attack. And maybe we can do something a little more efficient. So this is from a really nice paper by Daniel Cole. And this is showing again that planet to star flux ratio is a function of orbital phase. This is what I like to call a modeler plot, which is that if these are actually real planets, TRAPPIST-1b, blah, 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 you never actually see this phase 0.5 because the planet goes behind the star. You should have a dip there. But we're in the frame of the planet here because it's a modeling plot, which is great. Caroline knows what I'm talking about. Yeah, so what I thought was interesting about this is that for these planets where they can have atmospheres, but we don't expect a really extended one, the information content about the shift in the peak brightness is not so big, but there's a lot more information content in the total flux compared to when the planet is either down here or when it goes behind the star, and so it's being removed from the phase curve. So this is sort of an argument we can say, okay, if we're not going to get all that James Webb time, we can make a slightly more efficient observation. We don't get as much information, but we might get enough from just observing the secondary eclipse. So to sort of summarize the eclipse advantage, it's more efficient than a phase curve. You also don't need to worry about these unocculted star spots because the planet is going behind the star. So even if the stellar disk is not homogeneous, it doesn't matter. We're integrating over the whole thing equally throughout the whole observation. If you have a really quickly rotating star, fine, but generally that's not a problem because the observations are on order hours, not months or years. You also get what I like to call the CO2 bonus. So this is an illustration of the planet as it orbits the star, and over here is the secondary eclipse. So the planet is going behind the star. Whoops. No. And we're seeing the day side facing us, and then it goes behind the star, and we get this depth. And so this depth from before and after the eclipse to during the eclipse, this is telling you how much light from the star plus planet system was coming just from the planet. Going out to the infrared is really helpful for this because thermal emission can be a lot stronger than reflected light. And in addition, if you go all the way out to 15 microns, there is a huge CO2 feature, and this is really well known. It's in Venus, it's in Earth, it's in Mars. We've measured this. It's very well known. You know, there's issues with many alignments, but we know this feature is here. We know it's CO2. And if you have CO2, if you have an atmosphere and it has CO2, you not only get this cooling of the atmosphere because it's absorbing light in the optical and cooling down the day side, you also get absorption directly from the carbon dioxide itself. We don't know a priori if these planets have atmospheres or if they have CO2 in their atmospheres, but if they do, and it's a very common molecule, this is a sort of like extra, you know, we're trying to like stack our deck a little bit in our favor. Okay. But there's a challenge. There's always a drawback. These eclipse signals are really small. And there is also an uncertainty in when that eclipse is going to happen. I'll show you what I mean by that. This is the one hot Jupiter plot I'm going to show. So revel, bask in its glory. This is one hot Jupiter eclipse. This is WASP 18b with JWST nearest SOS. And this is again, so you see the planet-to-star flux ratio is a function of wavelength. And not only are they getting an eclipse, they're getting it at all different wavelengths. So the broadband is over here that I've highlighted for you, exquisite. You can see by eye. I don't even know how much data processing is in here. And then you can actually just pull out, oh, well, what does it look like over here? What does it look like over here? And you can, you know, these are just little examples of other eclipses, super clear. As you get even farther into the infrared, you can actually see that curvature coming from, you know, the day side coming in and out of view as it goes behind the star. So this is awesome. There's a lot of great science you can get out of this. This is one hot Jupiter eclipse. And this is the broadband. This is 5 TRAPPIST-1b eclipses stacked together. And this is actually a really high signal to noise detection. So this is like, we're solidly seeing it both at 15 microns and at 12.8 microns, 5 eclipses each. And I'm just saying this because I'm going to try to, you know, down the road, sell you on maybe putting 500 hours to doing more of this. This is why we would need so much time. And there's also a lot more data processing that goes on here. And you can see there's these kind of little, you know, these are not perfectly clean time series once you go to these smaller signals. The other issue, as I mentioned, is uncertainty in catching the secondary eclipse. Secondary eclipses have never been observed for rocky exoplanets around M dwarfs before James Webb, with one exception with Spitzer. That was because it was super, super hot. Generally, the secondary eclipse is just too shallow to see with pre-James Webb instruments. Now, if you have a planet on a circular or almost circular orbit, you have no problem. So here's James Webb, and it's looking at this little system, not to scale. But we know when the transit happens because we've detected the planet in transit, and you say, okay, I know the transit, means I know the period. I'll just look 1/2 period later, and there's my eclipse. That's great, we can just do that. But the reality is actually a little different. I mean, this equation has been simplified because there's actually a dependence on other orbital parameters, namely the eccentricity of that orbit and the argument of periastron, how that orbit is oriented relative to our line of sight. If you have a substantial enough eclipse of an eccentricity and an unfavorable argument of periastron, you can look 1/2 an orbit time later and there is no eclipse. The planet has not actually gone behind the star. These are a little bit exaggerated in terms of like the degree of that eccentricity, but this is a real problem. And if you're off, you know, if an eccentricity means you're a little unsure by 2-3 minutes, that's fine. We're already observing for a few hours. But for longer period planets, this becomes more and more of a problem because even small eccentricities mean you might be off by hours. And so that really eats into the advantage of just going for the secondary eclipse over like a phase curve. So we need to solve some system parameters to schedule observation. Yeah. Okay, I want to go through a few JWST results for rocky exoplanet atmospheres in secondary eclipse. When I gave a talk like this about 9 months ago, I just said all JWST results. And in those 9 months, there's now actually too many, and I can't show you all of them. So I'm going to show you my favorites. If your favorite is not here, I deeply apologize. Okay, so here's GJ486b. If you'll remember from the talk, we got a transmission spectrum of GJ486b. There is some ambiguity about if water was in the planet or the atmosphere. Megan Weiner-Mansfield and her team, well, they said, okay, let's definitively figure this out. So there were 2 secondary eclipses of this planet. This is a really nearby system. So you get the best signal to noise we're going to get. And you can actually pretty clearly see the eclipse there. This is one of our best systems. And that is a very deep eclipse that they measured. And Megan made this figure where you have this heat redistribution factor, so basically how much heat can be moving from your hot day side to your cooler night side. There's a function of bond albedo. This is how reflective sort of surface or an atmosphere might be. The point is even if you don't know what's in the atmosphere, you can kind of shuffle these parameters around and cover kind of like theoretical atmosphere, you know, with some unknown content in there. And what she's showing here, that at the 1 sigma or median level, her data would look very much like the moon or Mercury, both airless bodies. To 3 sigma, she is just ruling out a Martian atmosphere. And a Martian atmosphere is much, much lighter. It's about 6 millibars and CO2 dominant. So to actually be able to address an atmosphere that sort of unsubstantial is kind of amazing. This really rules out an Earth-like atmosphere, 1 bar of surface pressure, and really, really, really rules out a thick Venus-like atmosphere. So this technique works when you have favorable targets, and it can get us down into the regime where we're actually addressing atmospheres that maybe not compositionally, but in terms of their thickness and their ability to move energy around that look like solar system rocky planet atmospheres. I think it's pretty cool. This one's another one. So not all targets are as easy to observe. This is this is LTT 1445 AD. This is another rocky planet. It orbits an M dwarf. And these secondary eclipses were not as easy to pull out. So if you look at the kind of resulting figure over here, you are still able to rule out a Venus-like atmosphere. But things like Titan or Earth or Mars, these are well within the 1, 2, and 3 sigma kind of contours. So it's not a sort of nail in the coffin technique. And you can also get unlucky with your systematics, which I'm going to show you a little bit later. So this is basically the same plot I showed you before, except now we have emission. Spectroscopy is the same thing as transmission, but just for when the planet goes behind. And these are now planets for which we've been able to rule out 10 bar atmospheres or greater. In some cases, as high as 1 bar, or even like GJ486b, down to sort of Martian, 6 millibars. But to just sort of even it out, it's like none of these have Venus-like atmospheres. And then we said, okay, let's do this 9 more times. So this is the Hot Rock Survey, which I'm the proud PI of, along with my colleague João Mendonça, who did all the modeling for this effort. And encircled here are the planets that were included in this survey. And I'm going to show you some results. So this paper, which was just accepted last week and is now in press, this is by Pluno Lust, who is a grad student at Technical University of Denmark, where I did my postdoc. This is the weirdest data set. People have come to me very concerned about this technique with James Webb, and they point to this, and I'm like, truly, this was the worst one. But the data came in first. We don't know. Yeah. Anyway, what I'm showing here is that so note that we got 2 secondary eclipse observations because that's how many I calculated we need to address the bare rock case for this planet. However, this one has a very strange, it has this very wiggly thing in it. And Pluna has highlighted this for you by putting this little sinusoid there. That level of that sinusoid is much bigger than the depth, the eclipse depth we're looking for. It's actually about the same, but it means that if there was an eclipse in there, it would be hidden in this time-dependent systematic. Which she was not able to remove, so for now, we're just not using that eclipse. In the other eclipse, in the first one we saw, there was a hint, there was a detection that was favored over a flat line, although not to a full 3 sigma, so like 2.8 sigma. So there's a sort of 2.5 sigma detection where we expected the eclipse to be. But you know, we're not really sure. We're not super confident. If you plot this compared to some models, so here we have the eclipse stuff is a function of wavelength. Here's our CO2 bonus, and as you can see, the data point sits low compared to the bare rock case, which would be up here. In the review process, Plune very helpfully put this line here. So this is the 3 sigma upper limit. And so as you can see, with this one eclipse, we're not giving a statistical significance to this detection. If we'd had our second data set, supposed to do, but the second data set has all these time-dependent systematics. So this is a question mark. And we would really like to get more data. And if you were on the JWST talk, I hope you gave it to us. Other planets have been a little more straightforward. So this is TOI 1468b. This paper is in review. We had the report back a couple weeks ago. We got 3 secondary eclipses. Here they are stacked together. There's a clear detection. It's a little deeper than we were anticipating. So the gray line is like our best fit to those eclipse depths, but it's a little bit higher than our bare rock no atmosphere cases. Not hugely. It's within 1 to 2 sigma, depending on your reduction. But this is actually illustrating that there's a piece that's very tricky to disentangle, which is that this is the measurement. But in order to make these forward models, you have to provide stellar parameters. And we are not very good at knowing what M-dwarf stellar parameters are, which I will get more into. But just, yeah. So one thing is, yeah, maybe you can have a slightly hotter surface. There's some concepts called like thermal beaming, where you can get, if you have an uneven surface, you can get what appears to be extra, or what is measured as extra thermal emission. Or we could just not quite have our stellar parameters right. We're trying to capture it with these sort of, the line thickness is the 1 sigma error bar and the stellar parameter uncertainties, but even those, maybe we shouldn't trust so much. This is another one that also is pretty straightforward, but a really nice data reduction effort by Mark Fortune, who's finishing his PhD at Trinity College Dublin. These are 3 secondary eclipses stacked together of LHS 1140c. This planet has a famous habitable zone sibling. This is the neglected inner planet sibling. But this is a really nice definitive result of like, this planet probably does not have an atmosphere. And because this planet is close enough and warm enough, we are also actually ruling out Martian level atmospheres. This is like almost exactly like, looks like the figure I put in the proposal. So sometimes it's nice when like what you predict like comes true. But yeah, but probably a bare rock. Okay, so we've added a few more bare rocks here, and we have some more in prep that I've kind of put on this figure, but they're not ready for prime time yet. But what do we want to do with all these? Like, we have all these observations, and the point is we need to put them in context. So this was a paper led by Brandon Parkcoy at Chicago and Jacob E, who was doing his postdoc with me. Trying to sort of contextualize these planets as a function of sort of how hot they are, And then this R equals 1 line, that's sort of saying that the observation agrees with a bare rock, like no atmosphere. Okay, so they sort of were like, oh, it's kind of a downward trend here. And we've sort of messed that up a little bit. So, well, or maybe not. I mean, the error bars are big, but we have these planets that are consistent with bare rocks, even though they are somewhat cooler. And then we have this planet that again, not statistically significant, but that detection is real. This is way off, way off the chart in the sort of has atmosphere direction. And now we want to do this, we're going to scale up. Good to be scalable, right? So this is from a figure from the Rocky World's DDT. This is what I do as part of my functional work at Space Telescope. It overlaps really nicely with my research, so this was a good job for me. And this is going to take 500 hours of JWST time to sort of essentially scale up this process. Let's look at cooler planets and try to see if there are atmospheres there, but not just detect atmospheres. We really want to probe this idea of the cosmic shoreline. This is a made-up line that can just kind of be drawn through a bunch of targets in the solar system. But it's essentially saying that in a space of like X-ray and UV flux as a function of escape velocity, so you only need a mass and a radius to calculate a basic escape velocity. There maybe is a sort of division. There's maybe a line over which you can hold on to an atmosphere, which would sort of be down here. Maybe a time where you can't. The star is just too energetic, or you are just too small and not massive enough. You just can't hold on to an atmosphere. So the hot rock survey are these targets in red. So if you're sad to hear that they might all be bare rocks, my answer would be one that's very exciting. Bare rocks are very cool, and we should think about surfaces and things like that. But we've only probed the area of parameter space that we could access, and that is where we might, based on this solar system cosmic shoreline, we might say, well, okay, well, maybe these aren't the ones that would have atmospheres. And so we want to take this time and push down here. So that's what we're sort of working on. But this still has all the problems that I said before. Knowing when the eclipse time is, stacking lots of observations together. So that's what we are working on as we get this program off the ground. Okay. Oh, I don't have as much time as I wanted. The M dwarfs. And this is where it gets really fun, because you can actually detect things. So these were, I've shown this to you before. These are the Hot Rocks survey. There is a little companion survey called Hot Rock Stars, which takes a subset of these hot rocks targets and is getting the UV emission from their host stars. The reason we don't do all 9 is one is just too faint and far away, and the others already had UV observations. So we said, thank you very much. We will use that archival data, and this is the new data to collect. I'm not going to show you results from that survey because the data is not all in yet, but I can show you very similar data that we got for GJ486, which is the host star of the planet that we've been returning to. So one thing we want to say is a lot of these rocky planets orbit inactive, quote unquote, inactive M dwarfs. And when I say an inactive M dwarf, this is kind of what I think of as an exoplanet observer. So this is test data for GJ486, an inactive M dwarf. And you can see some wiggles, but even without that black line, you can see those transits by eye. Those little sort of blue lines, those are actual transits repeating periodically. And this is test data of AU-MIC. This is a famously active star. And there is a planet detected around here, but you'd be really hard pressed to pull out these transits by eye. The little B is where the B planet is. So we're not looking at these stars typically, not in the hot rock survey. There is a lot of work looking at these young stars, and that's very cool, but that's not exactly what we're doing. So when I say inactive, it's like comparing this to comparing that. But the picture is not so clear. So even inactive M dwarfs do not look like G stars. They're not just little G stars. They have a lot more high energy flux compared to their bolometric than G stars do. So these are, this is just sort of flux that has been normalized as a function of wavelength, and you can see the black is the sun, and the red is GJ699, which is Margaret's star. So you can see that even though the sun has more overall flux, more total flux across all wavelengths, the M-dwarf has a higher proportion of high energy flux. We're also not very good at predicting the UV flux, so this is actual data in the orange and red, and these are some models. And you can see none of the models are really matching the data as we go to the blue optical. So M-dwarfs are difficult once again. But why do we care about this extra high energy? And there's a really important piece here as it connects to rocky planet atmosphere. I guess any planet atmospheres, but if you have sort of a cross section of a rocky planet atmosphere, and while we're sort of running around down here on the surface, it is the upper layers that are most detectable by our observation methods. It's really hard to detect the surface if you have any kind of absorptive molecule, water, methane, CO2. It's very, these are very easy molecules to make. They're probably in an atmosphere if you can make an atmosphere. And so what you can really detect are these upper layers. And those upper layers are the most susceptible to high energy radiation from the host star, both in terms of escape in the upper atmosphere from X-ray and extreme UV, and even down here in the UV for things like photochemistry. So if we're going to detect an atmosphere and see what's in it, we really need to know the context of what the host star is doing to understand why we're seeing what molecules we're seeing, or why we're seeing escape that we're seeing. So we can do this. We can measure the high energy spectrum of these host stars. Mostly we can do the UV with HST, and we can do X-ray for some targets with Chandra and XMM-Noon. These stars, though, are emitting very few photons at these wavelengths. We're talking, you're literally counting the photons. You're counting numbers of photons here. It's not a lot. So those observations can be tricky. And then there's this other piece to it. So this is our friend GJ486. This is an inactive M-dwarf. I had a program that looked at the UV of this star. This was one visit 4 of our program, and these are 3 orbits with HST cost G130M, cost. So HST has Earth occultations, so it observes for 45 minutes, and then it goes behind the Earth, and then it can observe for 45 more minutes. So these are 3 45-minute observations with gaps of also about 45 minutes. And this star had been observed in the optical, because we detected this planet around it. And Jacob Bean said in an email, which I did not get his permission to reproduce, said that the quietest M-dwarf observed to date for extreme precision radial velocity. And yet, maybe you've already seen them, there are 2 huge flares that we observed in the UV in 3 45-minute chunks. And we can go and analyze those flares. We can fit a really nice model. You can get out flare energies. And we can compare those to work done by Park Lloyd for a sample of M-dwarfs. Now, I want to be clear, this work by Park was from a statistical survey designed to look for flares. To compare my data, which was just to measure the UV, to a data set where they had sort of like equal observing time and they spaced it out, it's a little disingenuous, I know that. But it's all we have. And if you look at a cumulative flare frequency as a function of the equivalent duration, so how much energy is in the flare, how much out of flare energy you need to create all that energy in the flare, GJ486 would be way up there. Again, this has not been corrected for, like, we should have got more baseline to really see if this was true, but we didn't know this would happen in advance. So is GJ486 like an extreme flare? I would argue we just don't really know enough. I posit in the paper that maybe M-dwarfs have these like activity cycles, and so you can just get periods of high stellar activity. But without more consistent time monitoring, we're not going to know the answer. This is my little advertisement for the ESCAPE mission, which is a SMEX mission, small I forget what it stands for. It's a proposal to make a satellite. This is led by Kevin France and Alison Youngblood. Small explorer mission concept, to look at the EUV and the FUV of a ton of stars, all the way from F down to M, and then also do deep monitoring, so long baselines of about 24 targets of interest to really get their flare rates and coronal mass ejection frequency. We're not going to be able to do every star. Probably, we're not even going to be able to do most M dwarfs. But if we could even get one, we don't even have one example of this, especially for quieter. So I'm really excited about that. And we're going to keep doing this in the Rocky Worlds program. So these are the same plan I showed before. And I'm just saying that we're getting 250 HST UV orbits along with the JWST time, so that when we choose some of these targets, wherever they are in this parameter space, we're also going to get complementary UV observations. We might not know what to do with those UV observations right now, but if atmospheres are detected, eventually we want to have that data in hand for the specific host star. And even though it's just a snapshot in time, it's better than nothing. So to conclude, we are making a big push to try to figure out if rocky planets or M dwarfs have atmospheres. It is extremely important. I think it's extremely important to understand M dwarfs if we want to understand their rocky planets. And thinking even farther into the future, all of this is groundwork for missions that want to actually try to detect habitable zone exoplanets around G stars. And even though they might not seem related, we need to hone these techniques now. We need to know how common rocky planet atmospheres are in the M dwarf regime to inform how common they might be around other stars like the sun. And this is just a really great multi-mission way to do it. So thank you.
We have time for some questions for Hannah. Mike.
I have a question about the kind of pre-made sequence of M dwarfs.
Yeah.
Because it's great if they're maybe not active right now. But this extended pre-made sequence, isn't that a problem for atmospheric escape, even if the planet would be safe now?
Yeah, that's really right. So M dwarfs have two problems, right? They have a really extended pre-main sequence where they have this high X-ray flux. The problem is we don't know exactly the evolutionary history of an individual star. We have sort of bulk trends. So there's like a saturation phase where you have like a lot of X-ray flux and then an XUV flux, and then there's sort of slow decline. And this has been measured, and it's different for like early M's versus later M's. But because it is so difficult to determine the age of M dwarfs, this is a problem. The one thing I will say is that because we're not looking for primordial atmospheres, we're pretty sure these planets, I would say we're like as sure as you can be with scientific, caution. These planets don't have hydrogen helium atmospheres. So whatever that X-ray flux was, that's gone. The question is, what is the flux now, such that could you outgas a secondary atmosphere, perhaps 2 billion years in, when the star has become less active? Maybe. But that's a good point.
Other question, John.
Yeah, I have a question about the H curves. Can inaccurate eccentricity measurements can mimic these offsets in the energy peak?
Yes, but then you would know when the eclipse is. So when you see the eclipse, that's why phase curves would be so great. If you can do the whole phase curve, you then know exactly when the secondary eclipse happens, so you know the time between the transit and the eclipse. And there's actually a really nice paper by Alexandra Mahajan and Jason Eastman that if you can actually get that constraint from the planet, that actually can fold back into your stellar parameters. You can actually get stellar effective temperatures and radii down to like 2 or 3%. If you don't know how, you should read the paper. There's some cool tricks you can do when you have big planets. Yeah.
Melanie?
It looks like for most of the targets that we're not able to like rule out just a bare rock scenario, but is the will the signal to noise, or is this current signal to noise enough to make any statements about, say, if the albedo of the planet is different because of different types of surfaces, or if it's been resurfaced? Is it good enough to be able to make those distinctions, or are we still kind of?
So I am hopeful about that. My postdoc would say, no, there's no hope. He's very realistic. No, but he has a point, which is that naively we would say, oh, okay, well, there's no atmosphere. Let's go over to our geology friends. Sorry. Specifically, no. Let's what does forestite look like? What do pyroxenes look like at 15 microns, and trying to do that. There's a paper out really recently on this by Renu, who is on the paper, if he's not the first author.
Is it Heather's student?
Yes. Okay, I feel really bad. Please look it up. I'm finding. The answer is, it's actually, there's a huge overlap in this parameter space, and it becomes very degenerate very quickly. And the signal from the bare rock, like what you're getting from like the albedo properties, essentially, is actually even smaller. You get less information than for an atmosphere. I don't have the numbers to quantify that exactly, but that is like kind of an active area, I think, of research right now. And my thing is like, okay, maybe you won't be able to tell like this silicate from this silicate, but like focus on the bigger parameter space. There must be something, maybe, I don't know. Yeah. To be determined.
So if you have like a multi-planet system, kind of like we were talking about lunch, you can better constrain the orbital parameters of the system and maybe have better timing with the eclipse spectroscopy.
Yeah.
But do you have any issues with like TTVs throwing off the eclipse
Oh,
spectroscopy enough to like really kind of mess with your observations?
yeah. So so this happens exactly in the TRAPPIST system. So there's 7 planets all near resonance, and so there's active TTVs. But TTVs, as long as you can measure them, are predictive.
Okay.
Like you can predict when it happens. As far as I know, only Eric Agel does it correctly. But there, this is possible. Most multi-planet systems, though, are not in these resonances.
Okay.
Now, whether that points to different formation pathways, there's a lot of research on that. But for example, for planets that are close enough, so they don't have to be in resonance, but they can still be in close enough orbits that you can make dynamical arguments to say that, well, if this planet, if this inner planet were eccentric, so say a planet 2 days was eccentric, and then there's a planet orbiting at 5 days, this system would actually not be stable on timescales of millions of years. And
Right.
Okay, maybe we're catching it, but on astronomical timescales, we would not be seeing it.
Okay.
So this helps us a lot. You can though say, well, is there, in those many myriad sort of formation theories, like does this somehow inhibit atmosphere having, or maybe it doesn't matter. There are strategies to like try to observe transits together or eclipses together. There's a program with TRAPPIST that tries to observe B and E both in eclipse at the same time to sort of like boost a signal. And yeah, that paper's not out yet. That's tricky, but we try. It's like it can be an advantage.
Okay.
It can also sometimes be a disadvantage, but yeah. Actually, also the one cool advantage is that if one has an atmosphere and one doesn't, or something like that, you can the common denominator is the star, so you kind of divide it out. So even though you don't know the stellar history, you know that both planets experience it the same, except at different orbital distances and therefore different temperatures. So that's been done to kind of test sort of planet atmospheres without, when you don't know what the stellar history was. Yeah.
Okay, we're gonna take one final question.
Okay, yeah, wait, what is like the outer edge and orbital separation of the furthest planets that you're observing?
Oh, in the hot rock survey,
Yeah.
that would be a 4-day orbit.
Okay.
So pretty short. Because they're hot
Slash
rock.
little.
They're
Yeah.
hot rock. But yeah, to go out to cooler planets, I mean, we know of habitable zone planets around M dwarfs, not that many, but they do, we know of course they exist, but we have detected some. That would be, so a habitable zone around an M dwarf is at about a 25-day orbit, like a mid-M. 25 days is still pretty short, that's like, every month is a year for that planet. But even that becomes difficult to detect. James Webb can't point at everything at all times of year because the sun gets in the way. Scheduling, there's a reality of like what can you fit into a schedule. You're trying to observe everything in astronomy. So those start to get really tricky, even though that M dwarf opportunity is like really helping you. It's still tough. So yeah. If